Yeah, drop, hey, huh.
Yo, what's up guys, this is 𝗪𝗪𝗟𝗟𝗟 and today we're playing ropfu from PicoCTF, another binary exploitation challenge. So let's go, we download the files, we see we have val and val and c. Don't forget, 𝗪𝗟𝗟𝗟𝗟 plus x val to make it executable. And let's review the source code. So right here we have a buff size 16, right? And then a val function which has a massive buffer overflow due to gets. And if you remember, man gets, never use this function. This function reads until a new line or an end of file. That means we can enter huge amount of data and overflow the buffer. And let's take a look at file. We see here it's a 32-bit executable, nice, and it's statically linked. Okay, that means we cannot perform attacks like ret2shellcode and stuff. We need to solely rely on the gadgets we have inside the binary. Let's first of all try and find the overflow offset. So we make a cyclic pattern of 100 and copy that. We run the program, enter it, and if we take a look at EYP here, 𝗪𝗪𝗟𝗟𝗪, and we see that the offset is at 28 bytes. Okay, and what else can we do with that? We see that when we crash the buffer, when we crash the program, at EAX we have some of our data already inside, and this is the start of our payload. And we also see that ESP has another part of our payload here. If we take a look at the cyclic offset we have, we see that this one until here is saved in EAX, and the rest, blah blah blah, is saved in ESP. This is what we're gonna abuse. We need somehow to jump to ESP or RAX, EAX, to actually execute shellcode, because if we see here, we see that NX is disabled. That means we can execute code on the stack, and that's exactly what we're gonna do. And let's see what gadgets do we have. For example, if we do ropfu-grep jump EAX, okay, we see lots of gadgets here. This one is the smallest one, seems promising, and the problem here is that it pops ESI before jump EAX. But if we take this gadget right here and we do xi this, we see pop ESI. But if we add 1 to this and make it B instead of A, we see that we have the jump EAX gadget. So this is what we're gonna take inside our solver. So jump EAX should be this. I'll also p3 to it like this. And what else do we need? Something like jump ESP, but unfortunately we don't have such gadget, ESP, and we see we get no results here. Fortunately for us, we can use the jump ESP opcode, which is like this. This will perform a jump to ESP using only these 2 bytes. So let's save it here. Jump ESP, so we have these 2 bytes right here. And then what we need to do, first of all, we need to set the context arts to 32-bit, because we are playing with a 32-bit binary. And after that, we simply need to enter our shellcode like this. So we do jump ESP first, which we also want to adjust it 𝗪𝗪𝗟𝗟𝗪 here, and we need until 28, which is the overflow offset. And here let's just add some knob slides. And after that, what we need the jump EAX gadget to actually jump right to our payload. So we're gonna use jump EAX, and after that we need to create our shellcode, and likely Bondtools will do this for us. So assembly shellcraft.sh, and if we do r.interactive, hopefully this will give us shell. Yeah, my bad, it was actually 𝗪𝗪𝗟𝗪𝗪 here. So let's run it again. ID. We still get nothing. Yeah. r.sendLine instead. And we see that we actually get shell here. So that was actually the payload. What we needed to do was find the overflow offset. It was at 28 bytes. This was easy to find. We just made a cyclic pattern and then see where it crashed. We checked the EYP. After that, we saw that our payload is written in EAX and ESP. So we needed to find the 𝗪𝗟𝗟𝗟𝗪 gadget. It was obvious there, we saw it, we found it. And after that, the tricky part was that we have to find a 𝗪ESP gadget, and that wasn't included in the binary, so we used the opcode for that. And the payload was simple after that. We have the 𝗪ESP opcode, and after that we adjust it with some nope slides, so the payload does not miss. And we have the 𝗪EAX gadget, and we write our shellcode, so we jump straight to it. And that's how we get shell locally. And let's also test it remotely. So we copy that, we put it here like this, and Python solver id ls, and we see that we managed to get the flag. So that was the challenge, guys. I hope you find the video useful and helpful. If so, leave a like and subscribe to the channel to support me, and see you in the next video. Bye!